So, hello everyone for this wonderful session. Krishna S. She is a faculty at Department of Computer Science and Engineering at IIT Bombay. She works in formal methods, a branch of theoretical computer science. In this talk today, she will introduce some topics of theoretical computer science through some puzzles. So, I'm sure you're going to enjoy it. Over to you, Professor Krishna.
Yeah, thank you so much, Shweta. So first of all, thanks a lot for this invitation. So this is the first time I think I'm going to be talking to, such young participants. So I hope, that I make sense at the end of it. So the puzzles was also kind of taking into consideration that I'm just going to introduce this area. Maybe some of you may have had exposure to this. So in that case, just bear with me. But I'm assuming like zero background. Okay, of course, I know all of you are mathematicians. So I assume that your love for mathematics is all that I need. And using that background, I'm trying to motivate this area called theoretical computer science, which is essentially mathematics in the disguise of computer science. Okay, so the idea is that if you're good in math, okay, then you're going to be very good in theoretical computer science. In other words, people who should do theoretical computer science are people who love mathematics or good at mathematics. Okay. So with this, I think let's get started. So the title is, it's only a peek. Okay. So because it's a very vast area. And my idea is to present some 2-3 areas within theoretical computer science, which I believe could be quite useful as an exposure. Okay. So as Shweta said, I'm going to just do this through some puzzles. So I have 5 puzzles which cover some 2-3 areas in theoretical computer science. So let's get started. Okay, so even before we get into any real problem, you must have played games like this with your friends, right? So you see 2 pictures on the screen. The question is, can you draw either of these 2 pictures, okay, without lifting the pencil while you're drawing it? So that, you start at a point and you keep drawing and you must come back to this point only and lift the pencil. Okay, is this possible for either of the 2 pictures? Yes or no?
Yeah, for the first
Yes,
one it's possible.
for the first one it is possible. Yes.
The
even
second
I
one
I
is
did
not
it.
possible.
Second one, it's not possible. Wow, that was really fast. Okay, so we are right. Left one, it's possible. Right one, it's not possible. So now I'm going to give these kind of pictures some name. I'm going to call them graphs. Okay. So these are not the graphs you have seen elsewhere, right? You would have done like in linear programming today morning, you were doing on graphs. So this is not that kind of a graph. These objects are called graphs. So what do we see here? We have a collection of dots and some lines joining the dots, right? So these kind of objects are called graphs. So here I have some there's just one representative slide. So this dots, I'm going to call them vertices. So a single dot is a vertex. So vertices is the plural of vertex. And the lines connecting the dots or the vertices are called edges. Okay, so a graph is such an entity which has a finite collection of vertices. And these vertices are connected to each other using edges. All right. So here you see some examples of graphs. So these are like pretty looking pictures, no? So you can draw several graphs as you please. This is just a representative collection. So why do we talk about graphs? Okay, now let's look at some real life systems, things that we see in day-to-day life, and try to understand that these are actually graphs in disguise. So first of all, let's think about internet, right? Today, especially after the pandemic, life has been proceeding based on the internet. So what is the internet? The internet is nothing but a collection of computers connected to each other, and you communicate with your friends, right, worldwide by using internet, right? So if you look at this, each computer can be thought of as a vertex, and the connections between the computers can be thought of as edges, right? So this, if I abstract the internet, it is a huge graph, right? You can think of the internet as a graph. Okay, so indeed, maybe some problems related to the internet, if I abstract or model them as a graph, and if I know some techniques of solving problems in graph theory, maybe I can make some contribution. Okay, so this is the first instance of graphs in real life. Now, second instance, social networks. I don't know whether you are too young to be on social networks. So Facebook, Twitter, right? There are so many possible social networks. So the idea that if you think of Facebook, all of your friends on Facebook are your connections, no? So in this picture, what I've tried to draw is you are a vertex. All your friends are vertices connected to you, let's say on some social network. Okay, so social networks can be thought of as graphs. Now let's continue. Somewhat more useful, or something again which we see in day-to-day life, are Google Maps, right? So suppose you go to a new place and you're trying to go to some destination you don't know, right? So you ask Google, okay, you type in the address and Google gives you a path, okay, how to go from your position to some other position. So in fact, Google actually suggests multiple routes, no? So you can say, give me the shortest route from this point to some other point. So if you look at this Google map, so any intersection that you see can be thought of as a vertex, right? And the connecting streets are the edges. So again, Google Maps are nothing but graphs. And the reason why Google Maps can compute and tell you that, okay, now there are multiple paths, okay, depending on the time available and depending on the transport you're going to choose. So essentially it is trying to work on a graph, and it is going to, talk about shortest paths or paths with some constraints, etc., etc. Okay, so again, a graph theory situation. So do I have more examples? Okay, I think I have just one more example. Now, this is an example of some paint software, okay? So many of us would have played with these kind of softwares. So typically one thing that we do is we click on some part of the picture. So in this example, there is a bird. If I click on the green part, right, and I want to change it to blue, okay? So how does the computer recognize that I want to change this green part into a blue part, right? So the computer basically works on these objects called pixels. So you can imagine pixels to be vertices. So when you click on the green part, basically what's happening is you're clicking on a pixel, and all the other pixels which are connected to this pixel is what is going to change from green to blue. So I've just tried to, draw on the side, this grid you see here. So these are the pixels. And if for example, right, when I click on the green part, all the other pixels or the nodes which are connected to this one basically can change to blue. Okay, so this again is an application of graphs which is used in paint software. So I think I have enough of real life examples for now. So now let's go back to our starting example.
Actually,
of
I was
drawing
able to draw
it
the
without
second
lifting.
one.
Who's this?
Dikshant.
Okay, so did you start from the point and come back to the same point without going over anything twice and without lifting the pencil? How did you draw?
Yes.
Because of course it's possible to draw, okay, depending on how you go about it.
I started from the leftmost point, that is the top of, means the left of the triangle.
Okay, and you came back to the same point?
No, I didn't come back to the same point. I came back to it and then I drew the arc as the last line.
Okay, fine. So let's see, there's another question. Neil?
Yes, ma'am.
Yeah.
Ma'am, I too was able to draw it.
Okay.
The same way as the Diksha.
Same way as Dikshant. All right. Okay. So
Yeah,
maybe
that is possible, but it's not possible for it to arrive at the same point.
Sorry, Vihan, what were you saying?
So even I did that, but the thing is, it should reach the same point after you draw it. That is not possible.
Okay, fine. The same point. It doesn't matter. It doesn't matter. Okay, so we will see a generalization of the situation, and then you will understand what are the exact conditions, right? So when I presented it first, I did not want to put too many constraints. I didn't want to say, okay, you should reach the same point. You should not, draw one line more than once. Okay, I did not put all these conditions. But maybe when you try it again, I want you to check two conditions. One, of course, you must start at some point, come back to the same point. This is condition number one. Condition number two, you should not traverse any edge more than once. Okay, so when you draw it, to come back, you should not basically go over the same thing more than once. Okay, so these two things, you can you can traverse more vertices any number of times. That is not a problem, but you should not traverse the same edge more than once. Okay, anyway. So the reason I started with this was I wanted to talk about a very interesting theorem in graph theory, which will generalize this puzzle and several other kind of situations. Okay, so this theorem is basically called the Euler's theorem. So what it says is, now you know what a graph is. So in this picture, do you see the labels A to F? Is it visible on the screen?
Yes.
Okay, great.
Yes, ma'am.
Yeah, so I've just called the nodes of the vertices A, B, C, D, E, F. Okay, so that when I talk about some paths, it is easy for me to, say what path I'm talking about. Okay, so an Euler circuit in a given graph is nothing but a closed walk. Okay, what is a walk? A walk is basically you start at some vertex and keep walking. Okay, walking along the edges. A closed walk is a walk where you start at a vertex and come back to the same vertex. Okay, that is closed, right? Because I start and come back, it becomes closed. Okay, so closed walk where there is this extra condition that you do not walk on any edge more than once is basically what gives us a Eulerian circuit. Okay, so does this graph have an Eulerian circuit? Okay, Yash, you have a question?
Yes, ma'am, I have a question. Will you be sharing this PPT later?
Yes, absolutely.
Okay, thank you.
I saw one more raised hand. I don't see it anymore. So Neil, did you have a question too?
No, ma'am.
All right, great. So now I think we understand what an Eulerian circuit is, right? An Eulerian circuit is nothing but a closed walk where every edge is visited exactly once. Yes, Anand?
Ma'am, are we allowed to traverse a point more than once?
Yes, of course, right? It is okay
Okay.
to traverse a vertex more than once. You are not allowed to traverse an edge more than once. Okay. So now this graph that you see here, does it have an Eulerian circuit? Yes or no? Is it possible for you to start at some vertex, okay, and have a closed walk and come back to the same vertex without traversing any edge more than once? So does this graph have an Eulerian circuit? Yes or no? What do you think?
Yes.
Yes.
Okay.
Yes.
So here I have drawn one Eulerian circuit. So I start at A, then I go to B, then I go to C, then I go to D, E, F, D, E, C, F, A. Okay, so this is an Eulerian circuit. So notice that I have indeed come back to some vertices more than once, but I have not visited any edge more than once. Okay, so since I can demonstrate one Eulerian circuit, one closed walk, this graph has an Eulerian circuit. So now I have some more examples. So let's look at all these pictures one by one. So the leftmost one is a star. So the question is, does it have an Eulerian circuit? I have actually depicted one
Yes,
below,
ma'am.
right? So I start with A on the top. So I can go A, D, C, B, E, A. So there is an Eulerian circuit. Now look at the second picture. There's a triangle and a line below. So I'm saying this does not have an Eulerian circuit. Do you agree with me?
Yes,
Yes.
So why do you agree with me?
because
is
we
not-
cannot
There's no
go
way
to
not a
the
closed.
You have to repeat the rules in order to guess it.
It's not a
There's
closed
no way
figure.
to an open from the ABC triangle to the D.
Exactly.
There aren't
I
any
cannot
edges that
fly,
connect
right?
the
I cannot jump. I cannot jump from C to E, right? There is no connection between C to E. That is why this does not have an Eulerian circuit. Okay, Surya, Anand, your hands are raised. Did you have a question?
Actually, I had for the last one.
Same.
Okay, so should I go back one slide?
No, in this
No,
figure,
no.
the last one.
Okay, the last one. All right. So, okay, so the last picture, you think there is an Eulerian circuit.
Yes.
Yes, ma'am.
So what is it?
B to D, E,
B to
then
D.
C, then D, again B, then A, then C.
B to D, then E, then C,
Yes, then B, then A, then C.
then B, then C.
A, then A, then C.
Okay.
You're not starting and ending at the same point. Yeah, we need to start
That
and end at the
was
same
not in the definition which
It
was
is
given.
there.
in the-
It is.
A closed walk. A closed walk means you start and end at the same point, right? So, of course, if you do not start and end at the same point, it's possible. But since we need a closed walk, it's not possible. Is it okay now, Dikshant? Does it make sense?
Yes, ma'am.
All right. That's fine. You know, definition, sometimes when you see for the first time, maybe you don't internalize all the whatever consistent parts. All right. So now I think most of us, I hope, understand now when you look at a graph, if you know the definition of what an Euler circuit is, you can say whether the graph has an Euler circuit or does not have an Euler circuit. Okay. So now the question is the following. When does a graph have an Euler circuit? Okay. Yes, Kanishk, go on.
Ma'am, does it depend on the number of vertices having odd number of edges?
Very nice. Okay.
I think if it has more than two odd number of edges, two vertex have odd number of edges, it will not be an Eulerian circuit.
All right.
Yes.
Good thought. Good thought. Urvi?
Yeah, actually, I think so. If you have to have a closed walk, that means that you first cross from a vertex, like start, and then come back. So there would always be an even number of edges at
Excellent.
one vertex if it's a closed circuit, closed walk. So
Sounds
I
good.
think an Eulerian circuit would only have even edges on every vertex.
Very
I
good.
think.
Very good. Okay. Anahita?
Okay, this might be a very basic observation, but obviously the figure needs to be connected and not as this triangle and a line. That is a very basic observation, but yeah.
Very nice. Very nice. So I think you are filling up actually all the necessary conditions that is required. Okay. Anushka?
Yeah, basically same as what she's telling, but just that we have, like, for each point that we need an even number of edges so that we can go and return from different edges and not repeat anymore.
Sounds good. Very good. Shrutika?
Yeah, something similar, like every vertex should have exactly like even pair of connections, because otherwise at the end you'll have one last edge which you have not visited yet, so you won't be able to complete the path, or even if you visit it, you won't be able to come back to the starting point. So
great. Yep, excellent. Kirti?
Yes, ma'am. So the starting and the ending point, if it is the same, then it has to be even number for all the vertex. But when it is allowed to start and end at different points, but we have to trace it without lifting the pen, then the starting and ending points can have an odd number of edges.
Okay, very good. Mridula?
Yes, ma'am. Ma'am, something like what Kirti said, the starting and the ending points, whether they are the same or not, they must actually have the even vertices. But the middle points do not need to have even vertices because we have to travel, come back again. So there are chances when they have odd number of vertices. Like the image that we had before, the vertices of the square inside had odd vertices. Odd number of vertices.
Well.
Okay. So, okay. So are there any different answers from what we have heard? Parul and Meera, what do you have to say?
Mama, I also had to say the same, that if there are even number of vertices, there must be even number of edges to make it like this.
Okay, okay. So I think many of you have got the answer, okay, already. It seems to be that, so I am going to basically borrow from what many of you have said. So when does a graph have an Euler circuit? So now, as we see in this picture, the left one, so notice that, so I'm going to define one terminology, okay, so that it is going to help me further. So this already raised by some of you. I'm going to say a graph is connected if there is a path between all pairs of vertices, okay. So what is a path? So an edge is a simple path that connects just two vertices directly. A path can be thought of as, a sequence of edges that connects one vertex to another vertex. Okay, so the left picture, if you see, take any pair of vertices, there is obviously a path that can take you from one vertex to another vertex, right? So left graph is an example of a connected graph. The right graph is not a connected graph because, as I said, I cannot jump from C to E, right? There is no path. Okay, so that's a connected graph. Now, the second terminology I want to introduce is the degree of a vertex. So the degree of a vertex is the number of edges that is incident on it. Okay, so incident meaning, as you said, right? If you take any vertex, look at the number of lines that are basically coming out of that, the number of edges coming out of that, that is the degree of the vertex. Okay. So using these two terms, the degree of a vertex and the connectivity of a graph, now we can answer when a graph is going to have an Eulerian circuit. Okay, so I hope the terms are clear, right? Degree and connected, both are clear. Okay, sounds good. So in this example, just in case something is not clear, let's look at the left graph. So the degree of the vertex A is 2 because there are two edges incident on A. And if you look at it, every vertex has degree 2, right? That is the story of the left graph. Look at the right graph. So there are two vertices which have degree 3 and the other 3 vertices have degree 2. Yeah, yeah. There, I see a raised hand. Arul, go on.
Ma'am, I have a doubt in the first graph. There is the vertices B and E, and there is also one more point above that. Is that also a vertex? But you didn't mark
You
it
mean
as
in the
black.
star graph?
Yes,
Are you
yes,
talking
ma'am.
about
Yes, in
the star graph? Yeah. So the vertices in the star graph are A, B, C, D, and E.
What about the point above the D and E, but you didn't mark it in black? Is that also a vertex?
If I may, just
yeah, go on.
so he's talking about the intersection of the so-called diagonals. Yeah.
Okay. Yes. So whatever is not designated as a vertex is not a vertex. Okay. So it's just that, take it like this, no? When I drew it allowing the edges to intersect.
Okay.
But that's not considered a vertex. So in fact, that is another area in graph theory. Is it possible for you to draw this so that no two edges are going to be intersecting each other? Okay. Right now, that's not something that's bothering me. But in general, when you see a picture like this, whatever is this, whatever bold dot or however is your representation, right? Whatever you are designated as vertices are only vertices. The points of intersection are not considered to be vertices. All right. Great question. All right. So now,
here the devices like any mobile phones.
Sorry.
Ma'am, it's like DNC or any devices that connects.
Yeah. So exactly, right? So if you try to think of the internet, okay, on this example, you can imagine A, B, C, D, and D to be computers, right? They are all connected.
So there is a possibility of having that as a vertex, and we are putting one more mobile there and connecting that mobile with C, E, and D. Is there a possibility?
Yeah, then that'll be a different graph.
Okay.
Absolutely right. I mean, so this graph is just demonstrating some particular instance from real life. If you have a different connection, right? If you require more devices to be attached, that will give rise to a different graph, obviously.
Okay. Thank you.
Right? Because see, I mean, one thing that in all the pictures I've shown, okay, maybe because of my limitations in drawing only so many vertices, I have not like shown really huge graphs, okay? But the definition of a graph just requires that I need finite number of vertices and finite number of edges, right? The finite can be as huge as 1 million if you wish.
Okay.
Arushi?
Yes, ma'am. I noticed that if there are an even number of vertices with an odd degree, then you can make a path, but it won't end at the vertex that you started at. Is that correct?
Yep.
Okay, yeah.
Arjun, go on.
Ma'am, I think I have a reason for why you can't have an odd number of vertices.
Odd number of vertices?
Ma'am, like an odd number of connections for a vertex.
Yeah, go on. Yes.
Ma'am, so I think it's because every time the path comes into the vertex, you need another connection to take the path out of that vertex.
Excellent.
Which means the number of connections has to be multiple of 2.
Absolutely right. That is a very good reasoning. Excellent. Yeah, that's exactly what I was going to say. I will of course say it for the whole audience, but you're spot on. Sounds good. Okay, so assuming we are all together with respect to what it means for a graph to be connected, what it means for the degree of a vertex. So here is the theorem by Euler. What the theorem says is a graph has an Euler circuit if and only if it is connected and every vertex has an even degree. So the reason is exactly what was said just now. Intuitively, if you think about it, every time you are at a vertex, remember you have to traverse all the edges that come out of each vertex. So this is one of the conditions, right? For the closed walk, I cannot ignore any particular edge. So anytime you come to an edge, if you leave it, okay, now, unless and until you have another way of whatever, coming back to it, right? You cannot basically ensure that you do not walk on any edge more than once, right? So that's exactly the reason. Whenever there is something to go out, I need something to come in so that I finally come back to the same spot as I started out with. Okay, so this is not a proof. There is a proof for this theorem. What I'm saying is not a proof, it's just an intuitive argument. Arjun, you had something more to add? Okay, it seems to, yeah, go on.
No, I didn't have anything.
All right, sounds good. Okay, so this is the theorem of Euler. It's a very famous fundamental result in graph theory. So now coming back to our starting pictures, okay, of drawing without raising hands. The left one has an Euler circuit. Why? Because you look at every vertex in the graph, they all have even degrees, right? Whereas if you look at the graph on the right, there are some vertices which do not have an even degree. Therefore, the graph on the right does not have an Euler circuit. Yeah. Does that make sense?
Yes.
Okay, there is somebody who wants to join the waiting room. Okay. All right. So now let's see, there is something more interesting, okay, than what the example I gave you. There is a history behind this Euler's theorem, okay. So this is a very old story which happened in a city called Königsberg. Okay, the Königsberg bridges problem is a famous one. So the emperor or the ruler of Königsberg had a very, weird question to the residents of Königsberg. So what you see here is the river Pregel. The blue part is the river Pregel, which flows through the city of Königsberg. And there are 7 bridges which go across the river. Okay. And of course, there is, of course, the remaining city is shown, okay, between the bridges, between the river, you see the remaining city. The emperor's question was, can you start at some region in the city and come back to the same point after traversing every bridge exactly once? Okay, the question is clear, right? The emperor's question was, you start at some point. You can start anywhere, okay, anywhere in the city you can start. But you must visit all the bridges exactly once and come back to the same part of the city where you started out. Okay, this was the question of the king. So now we are going to look at it as a graph. We are going to abstract this entire city as a graph, and we are going to use Euler's theorem to answer this. Okay, this is the goal, obviously, right? So the first thing is, there is a lot of garbage in this picture, right? I don't care how the regions look like. I don't care how many buildings are in a region, right? All that it matters to me is I started a region. And then my question is, can I come back to the region? Okay, is it possible for me to start at some region, come back to the same point, having gone through all the bridges exactly? So on the right, what I've shown is an abstraction. So the green parts are basically the regions. The river is still shown in blue and the yellow bands represent the bridges. Okay, so this is the first abstraction. Now the second level that I'm going to abstract is I'm going to draw it as a graph. So how can I draw it as a graph, right? Any suggestions on how I can draw this as a graph, this abstracted thing?
The green region should be the vertices and yellow should be edge.
Like every connection between a place where 3 bridges join, you can make it as a vertex. And you can keep the bridges as the edges. Like it's not necessary like you have to draw the rivers or any of those stuff. You can just keep the...
Exactly, right? Yeah, the river also can vanish when I finally draw the graph. I don't
Even
care.
the regions are not necessary. You can just keep them as dots.
Exactly. I just need to put my points of connection and the connecting edges. No, that is all which matters. So the bridges will become the edges and the regions should become the vertices of my so-called graph, right? So let's see if you agree with this picture, all right? So let us see. So the top green region and the bottom green region in the picture, I think they are depicted by the top and bottom blue vertex. Do you agree with that?
Yes, it's the same figure.
It is the same figure. So if you are able to see that the top and bottom green become the top and bottom vertices, there is an in-between ellipsoidal region, right? That is now captured as the whatever, another vertex. And the rightmost region is the rightmost vertex. And I just look at whatever bridges were connecting two regions. I just draw the edges appropriately. Now this has become a graph. And now I'm going to ask Euler's theorem. Okay, now tell me whether this graph has an Eulerian circuit. I just look at the degrees of all my
All
vertices.
degrees are odd.
So yeah, so this graph does not seem to have the property that all vertices have even degree. Therefore, it does not have an Eulerian circuit. Therefore, it is not possible for me to start at some point and come back to the same point, traversing all the edges exactly once. Yes, Anahita, go on.
Yes, ma'am. We have here considered the green area to be the vertices, but instead, can we just consider the bridges to be the vertices and do the problem instead in that way?
Okay, so then how will your graph look like? And remember, our point was to use the Euler's theorem, which tells us that you can traverse every edge exactly once, okay? Now,
Yes,
if you make the bridges to be vertices, right? First of all, it's not clear how Euler's theorem can be applied, because according to Euler's theorem, you can traverse one vertex more than once. You see that, right?
Right. Okay. Okay. Got it then. Got it. Yes.
Yeah. Urvi?
No, I just wanted to.
So did you have a question or you're good?
No, I don't have a.
All right. Okay. So does this make sense? The story, this is an old story. If you just Google, okay, Königsberg Bridge problem, you will see a nice Wikipedia article telling you about the story. And they will also tell you how, this was solved using graph theory. So how Euler answered the question using graph theory and all that. Okay. So are we good? You are with me so far?
Yes.
Yes, ma'am.
Great. So I'm done with my
Ma'am,
first
1 second, can you go back, ma'am? 1 second.
Yep.
Okay, ma'am.
Okay, Anahita, you had something more?
Yes, yes. So just a confirmation. So we are considering the bridges to be actual the edges, and therefore we can't travel through them once more. Or yeah, that's what is the logic, right?
Exactly, exactly.
Okay,
Right.
yes.
See, my goal was to apply the Euler's theorem. So you see, this is this is a very good question, because see, I have a real life problem. I am trying to translate the real life problem into an abstraction. In my case, it's a graph. Okay. So now if I should be able to apply a theorem which I know in graph theory on my abstraction, then my abstraction should basically, capture whatever, the details I need essentially, right? In the same manner, so that I can apply the theorem in the right manner, right? So since I had in my mind, I had to use the Euler's theorem. And according to the Euler's theorem, I know that every edge must be traversed only once. So keeping that in mind, my natural tendency is to say that, okay, the bridges which the king has told me that I can cross every bridge exactly once should represent the edges, right? Makes sense, no?
Right, yes.
Okay, Urvi?
Yeah, I was actually wondering whether Euler's circuit can actually have a real life application right now, because you have to traverse every edge exactly once. So what is that an application in Google Maps or something? It's something similar.
See, Google Maps also, you can think of it as an application, right? Especially if you want to think of shortest paths going from point A to point B, okay? So it is obvious that nobody would want to walk the same path more than once, right? To create a shortest route from one point to another point.
Yeah.
But then actually, to answer your question, the shortest path problem is also a different question in graph theory. Okay. So Euler's theorem does not, of course, answer all the possible problems. This is just one motivation for this theorem. But there are algorithms which compute the shortest path between point A and point B. There's a shortest path algorithm, which is actually, you can imagine Google Maps is actually using that algorithm. It is also true that Google Maps abstracts, these whatever real life maps as graphs and actually does computation on those. Okay. So the idea, the big picture is just to carry forward in mind that graph theory is one area which actually finds many applications in real life. Of course, the individual results that may be used may not be always Euler's theorem, obviously, right? Euler's theorem is just one result among the zillions of available results, right? Okay, so I see Akshat and Srinandan have raised their hands. So Srinandan, go on.
Yes, ma'am. So in this example, what are the vertices?
The vertices, so you see the right abstraction, the green regions?
Yes, ma'am.
The green regions are my vertices. So if you notice the top green region, okay, and you see the circular or ellipsoidal green region, right, just below, which is enclosed in the river, right? You see there are these two bridges, right, connecting the top region and this in-between region.
Yes, ma'am.
So now you look at the graph drawn below. The topmost vertex represents the topmost green region. Okay. The leftmost vertex represents this inner circle. So you see I have drawn two edges, right? The two edges are representative of the two bridges in the above picture. Okay. And likewise, so now if you map these respective regions to the vertices here, you will see that, wherever I had an edge or a bridge in the earlier picture, that has become an edge in my graph.
Okay,
Make sense?
thank you.
All right. Okay, Akshat.
Ma'am, I had the same question pretty much, so you just answered it.
Great, sounds good. Okay, then I think we are doing good. So that's the end of my first puzzle. The Euler circuit theorem demonstrated is the end of my first puzzle. Now let's move on. So by the way, not all puzzles are on graph theory. Some of them are on graph theory. The others are on other areas of theoretical computer science. So next is now I'm going to continue with graphs, okay? But I'm going to do something slightly different. I think we all like coloring, no? I would hope so. So let's look at the coloring problem on graphs. So let me just pose the question first, okay? So you are given a graph. Now we know what a graph is.
In class.
Sorry?
We did this coloring lines and shapes thing in mathematical induction classes.
Great. All right. So you already know a lot of background. That makes my job much easier, right? All right. So the coloring problem says what, right? You have to color the vertices of any given graph using minimum number of colors so that no two adjacent vertices. Adjacent means connected by an edge, get the same color. Okay. This is the statement of the problem. Okay. So now here is a graph. So we can try starting to color. So I color the leftmost node or vertex red. So that means B and F cannot be colored red, obviously. So I color B green. I color F to be blue. Now I'm going to the next vertex C. I can repeat the colors because my goal is to minimize the number of colors used. So I can reuse a color. So I make it red. Now E, observe that the vertex E is connected to F, B as well as C. So I need a fourth color. Okay, so yellow. And D I can color with anything. Okay, so this required like 4 colors to color this graph. Okay. So here it seems the minimum number of colors needed is 4. So here is yet another example. So this is a very beautiful graph called the Peterson graph. Okay, so here you can see that I needed red, blue, and green. 3 colors were sufficient here. Yet another example. So in this example, let's forget the colors. I seem to have used more than 4 colors, right? Do you see why? Do you agree that I need 5 colors here?
Because
Because
every vertex is connected with every other.
Exactly.
Vertex is connected to every other vertex.
Great. Yes, yes, Kavin, go on.
I think the number of colors used is the vertex has 4 connections, so it is the total number of vertices is 5, and one vertex has connection with all the other 4. So if there are 6 vertices and the one vertex was connected with all the other 5, then we would need 6 colors. It depends on the connections of the vertex.
Sounds good. Sounds good. Yes, absolutely. Okay, Mridula.
Something as a connection to what Kavin said. So I guess the number of colors used is the kind of the highest degree of that particular point plus
Very
1.
good observation. Very good observation. Agreed.
The
Exactly.
first
So if you
one-
know the maximum degree of a vertex in a graph, that will also tell you the number of colors that are necessary. Right? Okay, so let's proceed. Okay, so now is there an application for graph coloring? Okay, so I don't know if you have seen this before in another session, but if you think about real life, okay, we use timetables in so many places, right? There's a railway timetable, your school has a timetable, right? Wherever you go, timetables seem to be like absolutely necessary. So here I'm trying to, create an example of a timetable. So, okay, this is not exactly a school timetable, okay, but let's say when you go to college, there could be many courses which, you can say that, okay, I like this course, I want to take this course. Okay, so now if you look at this picture, what this table is going to say is that there is calculus, topology, probability, graph theory, algorithms. And if I put a cross, okay, in a place, it means that there is more than one student who is interested to take, basically there is somebody who wants to take calculus and topology. That's why there is a cross in calculus topology intersection. Okay, so there is at least one person who wants to do both the courses. And likewise, calculus and probability, okay, there is at least one person who wants to do both the courses. Okay, so question is now, when you create a timetable, usually when you make a timetable, you would like to address everyone's preferences, right? So if I, for example, put calculus and topology in the same slot in my timetable, it is not quite okay, because there is this person who wants to do both the courses and they cannot do this course, right? So when I create a timetable, it better be that calculus and topology are in different periods, right? Different time slots. Okay, so this seems to be necessary. So now and timetabling seems to be a genuine problem, right? It's like scheduling. So can we do this? Can we address this? Okay, so of course I want to create a timetable with minimum number of slots possible. So can I do this using graph theory? All right. So this is an attempt of trying to, again, I'm trying to model this timetable situation as a graph. So I've taken my courses as my vertices. So C is a node which represents calculus, topology, okay, algorithms, probability, graph theory. And now what I'm going to do is, whenever I see that there is somebody who wants to do, let's say, calculus and topology, I'll draw an edge connecting calculus and topology. Okay, that seems to be my idea. So draw an edge for every cross. So I do that. So there is somebody common who wants both calculus and topology. So there is an edge connecting those. Likewise, calculus and probability also somebody. So there is an edge connecting that. And I just keep doing the same thing. Okay, so T and G, topology, graph theory, somebody wants to do both. So just finish drawing the graph in the usual way. And now once I do this, I'm just going to ask you to color this graph. Okay, so obviously with the idea that whenever two nodes or vertices are adjacent, you will give them different colors. And there is a reason to give them different colors because they represent potentially different slots in the timetable I'm going to create, right? So if I can find the minimum number of colors required to color this graph, I also should know the minimum number of slots in my timetable so that there is no clash between, somebody who wants to do calculus and topology, for example, right? Or any two courses, right? Anyone who is interested in like K number of courses, suppose, okay, K could be anything. After I create the timetable by finding the minimum number of colors required to color this graph, the timetabling should be perfect. Okay, so this is an application. So according to this particular coloring, it seems two colors are sufficient, right? Red and blue is sufficient. So I'll create two slots in my timetable. I'll say that, okay, calculus and graph theory can run in the same slot because nobody wants to do both of them. And likewise, probability, topology, and algorithms can run in the same slot because there's nobody who wants to do any two of those courses, right? So this seems to be a timetable I get from my graph coloring. Yet another, reason why coloring was studied is when we look at any map of any continent, or even if you look at country like India, different states get colored differently, no? Now there is an obvious reason for that, right? If you look at any neighboring states, if you color them with the same color, it will give an impression they are the same state, no? So it better be that neighboring states get different colors, right? So this is a map on a plane, and map coloring seems to be an interesting thing, right? I would like to color my map. So one question that I want to ask is, do you know how many colors are needed to color any map? Any thoughts on that?
5.
4.
4.
I think this is originally done using the British.
Sir, but how are we sure it is always 4 in different?
Yeah, very good question. How am I sure? I am not sure. Okay, I have not proved this theorem.
Previous map was the 5 colors.
It depends. I know the boundary of the map, so we can't judge it now.
Okay, so there are some, hold on. First of all, wait. Okay, so notice the statement of the theorem. The 4-color theorem says every map in a plane can be colored using 4 colors. Okay, now the term in a plane carries some importance here. Okay, so this is what, earlier in some slides, somebody had this doubt, no? When two edges were intersecting, they had this question, okay, does it mean there is a node in between or a vertex in between? I said no. And I also said, it's a different question of interest, whether you can draw a graph so that no two edges actually intersect with each other. Okay. Now there are some graphs for which you can do that, okay, which are called planar graphs. So a planar graph is a graph which you can draw on a plane so that no two edges will intersect. There are some graphs that are not planar, which you cannot draw unless and until two edges are going to intersect. Okay. So the theorem here basically talks about maps in a plane, and therefore, if you want to look at the corresponding abstraction, they would correspond to planar graphs, not to any kind of graph, right? Because obviously, if you think of this Peterson graph, right? It was a complete graph and it required right? It had like maximum degree was 5, so it required 5 colors. So maybe that is an example of a non-planar graph for which 4 colors are not sufficient, right? This is the point. But perhaps if you think of maps on a plane, if I abstract it to planar graphs, 4 colors are sufficient. Now, how is it possible? That is not something I'm going to discuss, okay? The proof of the 4 color theorem is beyond the scope of this talk, but definitely it's a very intriguing question, okay? How can you prove that correctly, okay? Did people make mistakes while proving it? Is a very good question, okay? So let's see the history of this, especially since you asked this. So the conjecture, okay, that any map in a plane can be colored with 4 colors was first proposed in 1852. There were several incorrect proofs, as one would expect, okay, in the early 1900s. The first correct proof appeared much, much later, 1976. And then in 1997, a simpler proof was given by Robertson, Sanders, and Seymour and Thomas. Okay, so the proof is same, but it's a much, much simpler proof. The first proof was super complicated. Okay, so this is just some history to the 4 color theorem.
So it took nearly.
Then you have a
No, I had a comment. It's just that I remember that this problem was, I think it was one of the first problems to be solved using a computer where they went through all the possibilities and said that's why it works.
Mm-hmm. So where did you come across this? You read it somewhere?
Yeah, last year when I was a volunteer for MDP, it was there.
Excellent. Dikshant, go on.
Actually, what if we draw means a vertex, and then to the left, right, top and bottom of it more vertex, and the central vertex is connected to the others, and apart from that no other vertexes are connected, then it needs 5 colors.
Well, so the thing is, I think what you're trying to ask is, given a graph, is it a planar graph? I think that is the question you're asking.
Yes.
Yeah. Okay. So this is again, something that I am not going to answer it right now in this talk, because it is a question that definitely requires some reading by itself. Okay. Given a graph, is it a planar graph? Because some graphs have been shown to be non-planar. Okay. Because there must be a technique, right, to say that, okay, because when I draw it on paper, I can draw it as I wish. I can draw with intersecting lines. So that does not say anything about whether the graph is planar or non-planar. Yeah, you agree?
Yes, ma'am.
I mean, basically, just the way I am drawing it on the slide or somebody else draws it on paper is not proof enough to say that it's planar or non-planar. No, there must be some condition under which you can say that these graphs are planar. And then the 4 color theorem says, okay, if a graph is planar, then I can color it with 4 colors, right? Basically. So that is what the whole story is. But anyway, my point here was just to motivate you, saying that, well, 4 colors are sufficient for planar graphs. And our application to real life is that, okay, any map you can see on a plane, which happens to be all the maps we carry with us, right? They're all on, I mean, they are printed on a plain paper, no? So they are all maps on a plane. For them, 4 colors suffices, okay? So that is the message of the 4 color theorem. Okay, so yeah, Vihan.
Yeah, like, for example, we can take a state, suppose, which has many bordering states in India. Like, for example, I'll take maybe Telangana. So it has 5 states bordering each other. So then there is, and the positions are such that there is no way you can color without one pair of states with same colors touching each other. What about that?
Very good question. I think, why don't you take a look at this as an assignment? Very good question. See, the 4 color theorem has been proved. Maybe you're trying to find a bug in that. That'll be really interesting, no?
Yeah, like I just checked out a map, and in that it had Telangana and I think Chhattisgarh at the same color, which is bordering.
Okay, so are you saying that they have given the same color to states which are bordering each other in your map?
Yeah, like
Okay.
it had the same color and it's bordering.
Maybe they shouldn't have done that, no? Do you agree? Don't you think so, that they should not have done that?
Yeah, but even I'm trying to think that it's hard to do without using it, right? Like there is no other, I don't find any way. I'll just check it again then.
Yeah. No, good. See, the fact that you're thinking has served the purpose of my puzzle. Okay. And obviously it is not something so easy also, right? So maybe there is something more to it and maybe you'll figure it out. Okay, I'll move on to Arul and okay, there was another hand which just disappeared. Okay, Arul, what is your question?
Ma'am, the one you showed on the like Petersman graph you showed on the first, right? Is it a planar graph?
Peterson graph. Let me see. Hold on. What's the problem with this animations? This one, right?
Yes, ma'am. Is it a planar graph?
No.
What do you think?
Because it has 5 colors. So, 4-color theorem said only planar graph has 4 colors. So,
very good. Yes. You're connecting A and B together. So you want to conclude that this is not planar.
And one, so planar graph means no 2 edges will be intersecting.
Exactly. You should be able to render it on a plane. Plane means, in a paper typically, right? That's how we draw it.
Yes,
and when you draw it, no 2 edges must intersect. Okay.
So
let me give you a keyword to search.
Okay.
Okay. Rather than Peterson graph. So just type K5. Okay. K5 on Google. Okay. K stands for complete. K5 is complete graph on 5 vertices. So Kn is the complete graph on n vertices. Okay. So just Google search Kn planar. Okay. Just see what it gives you.
Okay.
Okay, Mridula.
So all simple closed shapes are with proper edges or planar graph?
Yes.
Okay.
It's a comment to what was asked about Telangana in the Indian map. So, like, Telangana is bordered by 5 states, right? But it isn't necessary that every state cannot be repeated. Like, though they are connected, like we saw in the timetable part, like one was connected by 3, but all the 3 others could be the same color because they weren't connected.
Yeah.
So
yes,
we can.
That was I was.
It's basically like it's not necessary like those 5 states should be bordering exactly each other once.
Yeah, no, that's the point.
The alternate ones can be colored same when the Telangana can be colored in a color, and the alternate ones which aren't connected or aren't neighboring each other could be colored in the same colors. Like
That's
it will
true.
not contradict our point.
Yeah, that's the point actually. What I was trying to say, like I thought that at first, but then I tried to do it on my own, and I kind of think that it's not possible because
I did it.
I'll just send the image in the chat if that's fine. You all can check it.
You can.
Although on Google it uses 5 colors, but I did it using 4.
Able to do it in 4 colors, ma'am. I was able to
Because the rule says that if Telangana has n color, means a certain color, then its bordering state shouldn't have the color. But in its bordering states, 2 states can have same color if the bordering states are not adjacent to each other.
Yeah, sounds good. Yeah, that's true. This is exactly following our rule, right? To color a graph.
And when we do it in that way, we kind of limit it to 4 colors. We can complete it in 4 colors.
I sent a screenshot regarding that.
Okay, sounds good. Okay, so there are some people who seem to have done it in 4 and some people who think it cannot be done in 4. Okay, so let's see. Arushi, yes.
Ma'am, you said that it has to be a planar graph, right? Does it count as planar if I take a piece of paper and I like fold it around and make a cylinder?
Well, so the definition of a plane is what we know as a plane, right? Typically plane rendering, draw it on a paper.
Yeah, okay. And you can't fold the paper?
Yes, absolutely.
Okay, got it.
Okay, I'll just kind of work it out because of the fact that, okay, someone shared the screenshot, it has 5, fine. But how can you be so sure that that bordering, like suppose now here there are 2 greens, fine. But how are we so sure that the other state's bordering will not have the same green in it? So we'll have to mark out the whole India map for that, and that'll take time. I'll just try to do it.
Sounds good.
Maybe
Okay.
we'll take this as homework assignment now.
I guess so. Yes, absolutely. And more than just, trying to color the map of India, I would even encourage you, if you think this is interesting, to read up a bit. See, now that you already know what a graph is, okay? Now that you know the definition of a graph, I think maybe you can try to read what a planar graph is, okay? As I said, my objective is just to kind of, touch the tip of the iceberg for you, so that you know that, okay, here is an interesting area which probably you're going to fall in love with later on, okay? I'm not going to all the details since I have 3 more puzzles to cover. Okay, let's see quickly. Arul and Anahita, do you have something to say?
Is there a possibility of coloring a non-planar graph with 4 colors and limited with 4 colors?
At least we don't know, okay, of such a situation. So what you're suggesting is a new theorem so the theorem that you're suggesting, I'm going to say it, you can say if this is what you have in mind. There are some classes of non-planar graphs for which 4 colors suffice.
Yes, ma'am. So is that possible?
That's the theorem?
Yes, ma'am.
Yes, maybe.
Okay.
Maybe.
Ma'am, and one more thing, ma'am. My name is Kavinain, ma'am. My last name is Arul, so you can call me Kavi.
Sorry. Yeah. Kavi. Kavi is okay?
Yes, ma'am. Kavi.
Great. Janvi.
Yes, ma'am. We called that graph that you showed, the one with 5 columns, we called it K5. So a planar graph will be with K3 and K4.
K3 is a triangle.
Okay, so it will be mostly K4 then, if it has K4.
Yeah,
so,
K4. So K4 would be the square with the diagonals. No, that is K4.
Okay, fine.
Right. So basically, when I say complete graph, all that I mean is that every pair of vertices has an edge between them, right? Then it becomes complete.
Okay.
Yeah, Anahita?
Yes, as for the question which Bihan asked, I tried it quickly on a map of India and it really worked with the 4 color theorem. That's just I wanted to tell.
If you don't mind, you can also add a screenshot to the chat, because somebody else had added with 5. So maybe for the advantage of some people who possibly have not got it, maybe you can add a screenshot if it is okay.
Yes, sure.
All right, thanks. Okay, so I see that graph theory has generated a lot of discussions. I'm very happy about it, but I also want to talk about, if not all 5, at least the next 2 puzzles. So can we move ahead in the interest of time?
Yes, ma'am.
Sounds good. Yeah, I mean, I would be happy to, if we could break it up in another session, if that possibility was there, great, but let's continue. Now we have the momentum, let's not lose the momentum. Okay, so puzzle 3 is again on graph theory, and this is the last thing I'm doing on graph theory. With this, I am saying goodbye to graph theory for now. Okay, so this is like a very classical thing you would have heard, okay? If you take a party of 6 people, any party of 6 people or more, okay? At least 3 of them are mutually strangers, or at least 3 of them are mutually acquaintances. Very believable statement.
Ma'am, it is intuitively true only.
Yes, intuitively true only. I agree. So can you show this using graphs also? Is it possible?
Maybe
so this
we
is the
can
friendship
mark people
stranger.
as vertices, and if they are friends, then there is edge, and if they are not strangers, then there is no edge between them.
Okay, great.
So let's be a graph. The people would be the 6 vertices. If they are friends, then they are connected. If they aren't connected.
Okay. And so how are you? So, okay, so fine. So I understand. So you're trying to suggest the model saying that the 6 people are the 6 vertices. And if they are friends, you draw an edge between them. If they are not friends, do not draw an edge between them. And then, okay, so how do you model the fact that, 3 people, right? I need 3 mutual friends or 3 mutual strangers, right? So how will you model 3 mutual friends? Yeah, Meera.
Can we just take the friends as vertices and strangers as edges?
Okay. So then you are suggesting that people themselves are classified as both vertices and edges.
Yeah.
Okay. So go on. How would you continue?
Yeah, I just want to think on it. I just had an outline. I will.
Okay. Continue thinking. Continue. Let's move on to what others. Kirti.
No, we can take 6 vertices and connect the people who are friends with one color, and then connect the people who don't know each other, that is the strangers, with some other color.
Very good. Okay. Good thought. Yeah. So this is your starting point, right? Go on. Mridula.
The same idea as Kirti. Like if we have 2 colors, we'll easily be able to show whether they are friends or enemies. We'll be connecting with one color or the other. If it is a connected graph, it has to be connected. Any 2 vertices have to be connected. So the color is that what matters. So
all right.
No matter how we arrange, we'll at least have 3 friends or 3 strangers.
Sounds good. Okay. Aditya.
Yes, ma'am. Can you please show the problem once again?
You want to see the previous slide?
Yes, ma'am.
Yeah. So in any party of 6 people, either at least 3 of them are mutual strangers or at least they are mutual acquaintances, right? This is the statement.
So I had a doubt, ma'am, because like if this question is symbolical, then it is right. But it is if it is a literal question, then it is wrong, because like if there is a class of 30 people and out of 36 people are in a party, so obviously they all know each other.
Yes. Yes.
At
So
least
we have 3 of them
3
which are
mutual
mutual.
acquaintances. At least 3 mutual acquaintances are there.
Okay, sorry.
Yeah.
Got it.
Sounds good. All right. Okay. Urvi.
Yeah, I actually have a question.
Yeah.
So are we assuming that there are only 2 cases, mutual strangers and mutual friendship, or is it like something in the middle as well? Like
no.
Okay.
Yeah,
So
either
there are only 2
you
cases.
know someone or you don't know someone. That's it.
Okay.
Yeah.
Yeah.
Yeah. At least for now. Okay. Maybe we can have a different version of the problem where whatever, there's an in-between kind of relationship.
Yeah, we partially know that person.
No,
Okay,
as like
philosophical discussions. Okay, how well do you know somebody? Anushka.
Yeah, so basically, like what Mridula and Kirti said, that there should be at least one connection between the 2 vertices. So we can see how many connections are there, and we have 2 colors. So according to that, we can say the colors should be 3, at least 3 of them should be of one color. So by PHP maybe.
Okay, sounds good. Okay, so now I think I've heard everyone one round. So yes, so I'm going to go follow what you suggested essentially. So I'm going to say take two vertices. If the vertices represent strangers, color them red. Okay, between them red. Otherwise, if they're acquaintances, color them blue. Okay, so this is what I'm going to do. So now let's see. The theorem, I mean, if I want to just restate the theorem using graph theory, I want to say there is either a red triangle or a blue triangle, no? Because when I get a triangle of the same color, 3 edges of same color, it basically says, if I get a red triangle, there are 3 mutual strangers. If I get a blue triangle, there are 3 mutual acquaintances. Yes, Anushka, go on.
So what to
You're muted. Oh, okay, fine. All right. Okay, so now let's, just do the very easy proof. So I'm going to take some vertex P, some random vertex P. Okay, so remember we all agreed that we are going to connect every pair of edges, right? So obviously, if I pick some vertex P, right, I have totally 5 edges coming out of it because I'm having 6 vertices in total. So it's easy to see that at least 3 edges must be of the same color. So either I have 3 red edges or 3 blue edges, right? So I'm just depicting that situation when I have all 3 are red edges. So P is like one person, A, B, C are the other. So if indeed all 3 are red, this is how the picture looks like, or the picture will look like this when all of them are blue. Okay. Now my goal is to get either a red triangle or a blue triangle in both the situations. So let's see what happens, right? So let's take one by one the remaining cases. So let's look at the color of the edges AB, AC as well as BC. All right. So now suppose AB is red. Okay, if AB is colored red, I already have got my red triangle. I'm done. So suppose AB is not red, it is blue. Okay, let it be blue. Now let's look at the other AC and BC. So again, if AC is red, again I'm done. I got my red triangle. So let it be blue. Okay. So now it remains BC. Okay. If BC is red, again I'm done. And if not, I get a blue, in which case again I now
And
get
also
a
done.
blue triangle, right? So I'm always done basically. And you can repeat the same story on the second case where I had PA, PB, and PC are all blue. It's the same reasoning. Again, you will see you will either get a red triangle or a blue triangle, right? Mira, go on.
I just want to ask that if we can prove it using a hexagon, like drawing a hexagon, and using the same way, we will get 3 vertices as red and 3 vertices as blue, and then we connect these 3 vertices and making a triangle.
Okay, so for you, the connections are the vertices.
Yeah.
All right. Okay, so then what role does the edges play in your abstraction?
Basically, it doesn't play anything. I just use that hexagon to color those things. Like we did that square. Sorry, we did that triangle. Like just that. We are just using that edges to color the vertices. But then again, we are using those diagonals to prove the relation.
Okay, it's a different kind of modeling that you're doing, right? So I don't know what is intuitive, right? So, okay, this could be intuitive to many people because you're connecting. I mean, it's easy for, I don't know. It's intuitive to imagine that people are vertices and the edges represent connections. But for you, you're abstracting the connections as the vertices. So then what is not clear to me in your abstraction is if you have 6 vertices, you're talking about 6 connections, not about 6 people.
Oh, yeah.
Okay. Ishan, Kavinayan, Devanand. Ishan, go first.
Yeah, why do 3 edges have to be the same color? At least 3.
Okay, see, the theorem statement said that if you consider a party of 6 or more people, there are at least 3 mutual friends or 3 mutual strangers, right? Now, how do I model the term mutual, no? So if I have a blue edge between 2 people, it represents these 2 people are friends with each other, correct? So if you throw in a third person, okay, so think of A, B, and C. Look at this picture, no? So in this picture, look at the blue triangle ABC, right? So the blue edge between A and B tells me that A and B are friends, B and C are friends, A and C are friends. So they are mutual friends, no? You see that?
Yeah, but
so
we started with at least 3 edges are the same color. Why is that? Why can't it be 4?
No. That is nothing. No, that is nothing. Come on. You take any vertex P, right? And you, so totally have 6 vertices, correct?
Yeah.
Okay, now I have only 2 colors.
Yeah.
Okay, so the question is, you take a particular node, there are 5 outgoing edges coming out of that.
Yes.
Okay, now you have only 2 colors to color these 5 edges.
Oh, yeah.
Yeah, exactly. That's all. Okay, so that is nothing. That is just obvious. I mean, I have 2 colors, 5 edges, you color them, at least 3 will be the same color. That's all. Okay, Kavi.
Can you repeat it has 5, the statement it has 5 edges, but we at last see that there are 6 edges.
Okay, let me go back to the starting point. Okay, so what I'm saying is, totally there are 6 vertices, right?
Yes, ma'am.
Okay, now I'm picking some particular vertex, I'm calling it P. Okay, now we agreed that I'm going to draw edges from this guy P to all the remaining 5 people. So that will give me 5 edges.
Okay, ma'am, but here you drew only 3 edges.
Yeah, because I mean, I was only interested in taking these 3. You see that?
But the question was 6 people, right?
Yeah. I mean, see, my interest was to demonstrate a red triangle or a blue triangle.
Okay.
Correct. To achieve that goal, it was enough to consider these 3 red edges or these 3 blue edges. Of course, you are welcome to throw in the, the remaining people, no problem.
Okay.
Right, because I already got what I wanted by considering the subset.
Okay.
Make sense?
But so every person would have a connection with another person.
We are not even saying that. All that we are saying is that there are 3 people who are mutually friends among the 6.
Okay.
Or there are 3 people who are mutually strangers among the 6, right? So to achieve that, from this, P, A, B, and C, I can already achieve those 3 mutual strangers or mutual friends.
Okay.
You see that?
Yes, ma'am.
Yeah. Okay. Devanand.
I mean, in this case, there are only 4 vertices, right?
Yep.
Ma'am, but we need 6 people, so
exactly. So it is related to Kavi's question. This is actually related to Kavi's question, no? Because see, okay, of course you are welcome to add the remaining 2 vertices, right? No problem. Okay. So let's draw. Okay, let's draw Q and R as your remaining 2 vertices. So now you have all the 6 people together. Okay. And now what am I going to do? I am just going to observe that. Well, take any person among the 6. Okay. I want to talk about this person's relationship with the remaining 5 people, right? So
yeah.
Yes, that is the top line of the slide says you take any vertex, there are 5 outgoing edges coming out of it, depending on whether he's friends with A, friends with B, friends with C, with R, and with Q. Okay. And now I just realized that, okay, I am going to draw 5 edges, color them appropriately. But since I have only 2 colors, I just told myself that, well, 3 of them are of the same color. Let me just focus on the 3 edges of the same color and proceed with my proof. So in some sense, I did not use the fact that there are 2 more people who are there in the picture.
So in a sense, this must be true with 4 people as well, right?
This must be true with 4 people as well. Good question. Good question. So notice that to proceed, I have used the fact that I have totally 5 edges coming out of any vertex, and I have only 2 colors.
Yeah,
and
so it won't
therefore
work.
3 of them. Yes. So therefore, I have utilized the fact that there are 6 people.
Yeah, right. Got it.
Okay, Kavi, you had a follow-up question?
No, ma'am, I forgot to lower.
Okay. Anahita.
Yes, ma'am. So technically, in this case, we are using the edges as the relationship between them, between the people. And then we are taking a small scale example here just for explanation, and then we can use it on a larger scale as well. That's the point.
Correct. Absolutely.
And my another question was that, is it necessary to use all the people in that connections, or that, like Urvi said, can we just work out with 4 people even out of 6 people? Is that fine?
Yes. So yes and no. Okay. Yes, in the sense. So if you look at, so to proceed with my proof, I required 4 people only. Okay, here. But I did make use of the fact that I had totally 5 edges to talk about from any one person. Yes.
Right.
So the answer is yes and no. So because of the 1 yes, I did require totally 6 people.
Right. Okay.
You see?
Got it.
Yeah.
So if the problem is of only 4 people, then it will be true. But if that's a problem of 6 people and 5 edges need to be used per each, so that's
exactly.
Got it.
Yeah. Kevin.
Ma'am, so now we are only using 4 people to prove our fact. With this, can we assume that the other 2 does not have any relationship with these 4?
No, we can't assume anything, right? See, the point is, okay, now when I take P and you throw in the other 2 people, okay? Now, all that I'm saying is, I really do not care whether between P and those 2 guys, I had a red edge or a blue edge. That is all I'm saying. I really do not care because I needed to pick 3 edges of the same color, okay? And I just so happened to pick these 3. Now, there is a definite possibility that, okay, out of P, all were red edges. There's a possibility. And if it is a possibility, I could have chosen at random 3 red edges coming to Q, A, and R, maybe, right? It's just that, I didn't care about them because what I needed, I've got already. Does that make sense? Okay, Anushka.
Yeah, so over here with P, we have 3 vertices, and each of them we have colored with the same color. So, so we can, like, there can be other possibilities, like between P and A, there are P, A and B, they are strangers, and P is friends with C.
Yeah, possibly.
So that would be a different case, right? So, but we have considered all 3 red and all 3 blue.
Because see, that does not matter, right? All that I need to worry about is if I pick any vertex and look at all the 5 outgoing edges, right? I just need to keep this in mind that at least 3 will be the same color.
Okay, like that.
Yeah, so I'm utilizing, only that part to come to my conclusion to say, okay, from this I can get a red triangle or a blue triangle.
Yeah, so the first step is by PHP and then we prove using the...
Exactly. Yeah. Kavi?
I want to confirm that there are also possibility of having all the edges of same color. All are
Yeah,
neutral.
Absolutely. Absolutely. Okay. Yeah. I mean, that would be an easy case for me, right?
Yes.
So if, for example, I also knew that, A and B were strangers, okay, then, I mean, even before I begin, my proof is with me.
Yes, ma'am. You can draw like one edges in one color and another edge and other edges in another color.
Yeah, of course, right? Because see, so when I started this proof, I did not really worry about what color I could have between AB and BC and AC, for instance, no?
Okay. Yeah.
My starting point was based on a very simple fact that if you have 5 things and only 2 colors, 3 of them must be of the same color, right? That was all my starting point is.
Yes.
Right? So in some sense, I'm just taking the minimal, set of things I require to proceed. And that kind of, already helped me to go forward.
Yes. Okay.
Okay. So how are we? Are we doing good?
Yeah, perfectly well.
All right.
Yeah, was that question to me or to the students?
Well, in general. So in fact, I think I am not sure if I'll finish in 12 minutes.
No, so they have something at 6, and if they can get
no, I don't want to take so much time also, but I'm very happy with this interaction. It is going like amazing.
I can see that.
Yeah, it's awesome. All right, so now goodbye to graphs. I am going to the next topic. Okay, I can see that well, typically many people like graph theory. Okay, from what I have seen, and it seems to be the case from you guys also. So let's see if you like the next topic as much. The next topic is on logic. Okay, I think many of you would also like logic. So there is this great American logician, mathematician, magician, pianist, okay, Raymond Smullyan. So he has authored several very nice books on logic puzzles. So one of them is The Lady and the Tiger, and there are many, many more. Okay, I think it's a very good buy to kind of buy some of his books and read them. So what I'm having here as a motivation to another area in theoretical. So by the way, so graph theory is one area, okay, in theoretical computer science. By now, I think everybody would be clear of that. The graph theory is an area with several real life applications, and you need a lot of mathematical reasoning, okay, to do well in graph theory. So I think if you like combinatorics and if you're generally good in, this kind of reasoning, I think graph theory is great for you. Now, logic is yet another area in theoretical computer science, and I'm going to talk about that. So of course, to motivate logic, I'm going to start from logic puzzles. And the puzzles I'm going to talk about here are all Smullyan's puzzles, okay, taken from some or other of his works. All right, so now let's go to some fantasy island, okay? So there is this fantasy island, and there are only 2 kinds of people who live in that island. They are called knights and knaves, okay? So knights are those people who always tell the truth, and knaves are people who only always lie. Okay, so this is the characteristic of people. So, none of us can qualify as knights or knaves. No, we are sometimes truthful, sometimes we lie. So this is a very special island. Okay. Now imagine that somehow you got lost. Okay, you were going somewhere, you got lost, and you entered that island. So now the people whom you see are, wearing this, whatever, opposite kind of uniforms, okay? And you don't know what is the uniform of a knight or a knave. Yes, Srinandan.
Oh, I was going to answer the puzzle below.
Hold on. No, you can't answer
Yeah.
so far. Yes, if you know the answer, keep it, okay? For now, hold it. I know it's very hard to hold it, but hold it. All right. So now you meet two people. You just know them by their dresses, okay? A and B. And now A says, we are both knaves. And can you figure out in reality who's who? 5 people have raised their hands. Okay, let's go. Why can't I see anyone now suddenly? Hold on. Okay. All right. So Srinandan, being the first hand raiser, go on. Or wait for a minute, no? Just give everyone 1 minute.
Yeah.
1 minute. So, okay, with this information, A just said that we are both knaves. And as a listener, you have to apply some logical reasoning. And you must conclude correctly who's a knight, who's a knave. That's all. Pretty simple.
Both of them are
Yep.
of opposite. So only one is a knight and one is a knave.
One is a knight and one is a knave. Yes.
Okay.
Yeah. So, okay, Srinandan, go on.
Yeah, so because A is saying we are both knaves, like if that person was a knave, he would always lie.
Correct.
So both of them are a knave. So the person B is a knight. And person A is a knave.
Let's see what others say. Wow, there's a great race, show of raising hands. Anushka.
So,
ma'am, which Anushka? The first Anushka I see, Anushka Tonapi, who's raised hand. That's a topmost hand I see in my list of hands.
Okay, ma'am.
Yeah.
So we have to ask them a specific question so that you'll get your answer when like one of them lies and one of them tells the truth.
Well, here you are not allowed to ask them anything yet.
Because they may say the lie and you'll get more confused.
But no, but you have to ask them like a specific question. You can't like ask random
Like what
questions.
will the
I think
other
that's a
one
different
say
problem.
is the
Yes,
most
that is a
correct.
different situation. In this situation, let's say that, you have been dumbfounded. You can't answer. You can't question. You just listen and figure out.
So do
So
they
you
like
can
have a
follow.
conversation or something?
Yeah, we will come to that. That's a different puzzle. A variant of this where you talk is allowed, but now you cannot talk. Well, you can talk here, but not in the island.
Oh, okay.
Yeah. Okay, Urvi.
Yeah, so I considered cases. So let us say A is a knight.
Very
Then irrespective of whether B is a knave or a knight, A would never say that we are both knaves.
Correct.
So that those two cases are out. The next two cases that are remaining are that A is a knave himself.
Correct.
And so if A is a knave himself, then and B is a knave as well, then he would never say this because this would be true.
Correct.
And therefore the only option left is A is a knave and B is a knight.
Okay, good reasoning. Very good reasoning. Now, okay, so there are 18 people. I am short of time. So should we just go fast on this one? So
Yes,
did you
ma'am.
follow the argument given by Urvi, right? Sorry, that was the name, no?
Yeah.
Sorry. So the solution given by Urvi said this answer, right? A is a knave, B is a knight. And the reasoning suggested was that you consider both cases, right? What happens if you assume A is a knave, then do you get a consistent situation with the premise given to you? The premise given to you is that a person who's a knight will always tell the truth. Person who's a liar, a knave will always lie, okay? So the situation is assume that A is a knight. If you assume A is a knight, then whatever that person said, which means we are both knaves, must be true, but that immediately contradicts the assumption that A is a knight. Therefore, that cannot happen. Okay. End of story number 1. Now, the second situation is that assume that A is a knave. Now, if A is a knave, the statement he makes is always false. and he says we are both knaves. So that must be false, but that is still allowing you to get a consistent conclusion because A is a knave, he lies, he says we are both knaves. Now, therefore, that is a lie. Therefore, the other person is a knight. Therefore, the story must be that if two people are of different, okay, from the uniform, if they are different from different tribes, A must be a knave, B is a knight. Make sense? Okay.
Yes, ma'am.
All right. So is it okay if I proceed? I know there are so many, I know it's very tempting to kind of, go on with this, but since I have 3 more puzzles on knaves and knights of increasing difficulty, let's proceed. Okay. Sorry for not answering everyone. Okay. So here is again the same island, the same kind of people. Now we meet 2 people and A says B is a knave and B says both of us are knights. Again, you are not allowed to talk on the island. You can talk here. Okay. And what are they? Okay. The topmost hand is of Kavin. Go on.
Ma'am, I have.
Yeah, go on. Or okay, if Arjun, yes, Arjun gone. Smayan now. Okay, Smayan.
Yeah, so A says B is a knave.
Mm-hmm.
And B says both of us are knights. But if both of us are knights, then B is a knave is wrong, right? Because they have to be both knights, and a knight can't be a knave, obviously. So therefore, A is a knight and B is a knave, and A is telling the truth. B is a knave and B is lying because they are not both knights.
Mm-hmm.
Yeah.
Okay.
Yeah.
So does the rest of you agree with Smayan's reasoning?
Yes, ma'am.
Yes.
Yes,
Okay,
ma'am.
wonderful.
Yes, ma'am.
Excellent,
Yes,
right? So the reasoning says exactly that, right? If you assume A is a knight, and then he says B is a knave, that must be true, which is consistent with B lying that both of us are knights. So great. And if you assume the other way around, if A is a knave, then that would imply that B is a knight. But then B being a knight will not say that both of us are knights because A is a knave. Okay, so great. Okay, so I think you're getting the reasoning very well. So let's see a third situation here. Again,
Ma'am, I have a doubt.
Yeah. Go on.
Ma'am, what if there's only one person and they say, I am a knave? Then what are they?
They are
If there is
nothing
just
because
one
knave will
person
say
and I am a knave.
Definitely knaves.
Sorry,
Then they
sorry.
are neither. They can't be a knight, nor can they be a knave. The knave lies, whereas a knight tells the
If
truth.
there
It
is
isn't
only
possible.
one person, can I? If there is only one person and he says that I'm a knave, and that situation is not possible because if he is a knave, he always lies.
Correct.
And if he is a knight, he always tells the truth.
Correct.
So that situation is not possible.
I agree.
That's paradox again.
I agree.
Yeah.
Yes, very good observation. Very good observation. However, it's possible to have a person who says I'm a knight.
Yes, definitely, because that person will be
If he
telling
says that I'm a knight, then it's possible.
Then it's possible.
Then it's
Then
possible.
can you also say who that person is?
No, because he can be
No,
both
we
a
can't
knave
say, but
and a
we
knight.
can't say.
No.
That situation is possible, but we can't say. But if he says that I'm a knave, the situation is itself not possible.
Correct. Correct.
Like,
Very
ma'am.
good. Yeah.
Yes. So as Kavin said that we have to consider that a person is a knight and he says that I am a knight. That is also true. But if a person is a knave and he says that I am a knight, that is also true because knave always lies.
Correct.
And knight always tells the truth.
So basically what you're saying is that if you happen to fall into that island, if you see a single person who proclaims that I am a knight, then you are done for. Correct? Because you never know. Okay. So good. I think you're getting it spot on. Now, okay, what is your take on this? Okay, you see 2 people One A says we are the same type, B says we are of different types. What are they? So there is no taking knight or knave names. It just says same type, meaning either we are both knights or both knaves. And B says we are of different type, which means one is a knight, one is a knave. What do you think?
Krishna, this is Vinay
Yeah.
here.
Yeah.
Can I just request something?
Yeah, go on.
There are a few of them who have raised their hand, but who haven't spoken so far. So do you think calling out their names might be good?
Sounds good. Yeah, good point. Okay, so let me look at the list. Simran, can you go on?
A is knave and B is knight, because if A is knight, B would be also knight, but he should always speak truth. So he's saying some different by A, so he would be knave. So A will be knave, and he's saying some lie that they both are of same type. B is saying truth that they are of different types. So A is knave and B is knight.
Okay, so let's see. Karnam Javeri, do you agree with Simran's argument?
Ma'am, I couldn't hear Simran properly because of her background noise. So can I give my reasoning?
Okay, carry on.
So first we can assume that A is a knight. So he will say the truth. So the truth is that both of them are of the same type. That means both of them are knights. So whatever. So B is also a knight, and it will say the truth. So it is saying that we are of different types. But if both of them are knights, then they cannot be of different types. So that means A cannot be a knight.
Okay.
So if A is a knave, then it will say false. It will say the false thing. So it is saying we are the same type. So the true will be that both of them are of the different type.
Correct.
So and if both of them are of the different type, that means B cannot be a knave. So it has to be a knight. And the knight is also saying the truth that both of them are of the different type. So the A is a knave and B is a knight.
Good. Yeah, so sounds good. So indeed, it's true that A is a knave and B is a knight. Yeah, spot on. So now I'm moving to the last puzzle, okay, which is slightly more difficult than the first three ones. So again, you land up in this place and you see these guys standing at an intersection, okay. Now things are a bit dangerous. One road will lead you to freedom and one road leads you to sure death, and you don't know which road to take. Okay, these are the only two people standing there. So you have to ask one of them. Okay, now comes your chance to talk. Anushka Tonapi, you are wanting to talk to these people. Okay, now hold on. Okay. So now you know that one is a knight and one is a knave. This is all that you know, and that you figured out by their opposite, costumes. Okay, you can ask only one question to one of them. Now ask a question to one of them and get the road to freedom. So what will you ask and who will you ask?
Question, ma'am.
Yeah.
So does the one with the knave lead to death and one
No. Nothing like that. Nothing like that. No, nothing like that. They are just standing. Okay, and that's all you know. It doesn't say that knight is standing on the road to freedom and knave is standing on the road to death. It doesn't say that. It just says two people, these two guys from opposite tribes are standing at an intersection. What is clear is one of the roads, if you take one of the roads, it will lead you to sure death. The other road will lead you to freedom. You want to figure it out by asking one question to one person. That's it.
Can I answer?
So the thing is, irrespective of who you ask, okay, this is the thing to keep in mind, okay, because you don't know a priori who's who, obviously, right? Because if you knew who's the knight, you would go and ask him, obviously. You don't know who's who. So without knowing who's who, you should ask one question to either of them. So the idea is that whatever you come up as a solution, it must work irrespective of who you ask and irrespective of whether that person happens to be a knight or a knave. Okay, keep this in mind. All right.
You can ask one of them comparing what asking them about the other person.
You are welcome to ask anything you want. You can ask, is the other person good also, if you want. That's allowed.
How many
May I
questions can
answer?
we ask? Question
One.
is a bit.
One question, but as you said, it is okay to ask something involving the other person. That is allowed.
Can we like mass answer, or are you supposed to choose who's supposed to answer?
Say it again. What was the question?
Like, can I just answer it off now, or will you tell tell
I
a
guess
name and
now, in the interest of time, please go on. Whoever thinks they have
Can
a
I
solution.
answer?
okay,
just
fine. Like you go
I
to
can
a
answer.
person and ask, what would the other person say if I asked which is the right road? Then both of them will point towards the wrong road. You have to just go to the other.
Okay.
Correct. I am of the same opinion.
I did not
It is
get the
very
We can only
argument.
ask the question to
I
one
would
of
ask
them,
something.
right? We can't ask the question to both of them at the same
So
time.
we are asking to one only. He is telling what will the other one say
Okay.
without asking.
So this is what they said. Okay. You ask A. A could be either of them. Does not matter who A
Yeah,
is.
this is what even I thought.
I
There
have
is
another
no-
answer.
Yes.
My answer is like you ask A. If you ask A whether the road A is standing on is the road to freedom, would they say yes? If they say yes, you take the road A is standing on. If they say no, you take the road B is standing on.
Okay.
I did not
You don't know who
So by the way,
is the
right?
liar and who is the
There is this assumption that, okay, you see these two roads, okay, the roads have names, road 1, road 2, okay, the names are attached to the roads, okay. So this question is assuming that, okay, one road is called road 1 and another road is called road 2, okay. This assuming that. So now let's see, I don't know. So do you, so what do you think of this answer? People, this assuming that answer, who did not think of this, now when you see this, what is your take on this answer? Do you think it is going to work?
No, I think. I didn't understand how this.
Ma'am, can you just explain that once?
Sounds
so
good.
that-
Yes, of course, I'll explain it. So let's say the answer says you ask A, where A is whoever, right? I don't care who is. Will B means the other person, will B say that road 1 leads to freedom? The question is clear? So let's say Dikshant is A and Kavin is B. Okay, these are the two top people in my hand raisers. Okay, Dikshant is A and Kavin is B. So I am going to ask Dikshant. Dikshant is A. Okay, I'm asking, will Kavin say that road 1 leads to freedom? This is what I'll ask Dikshant. Okay. Now Dikshant will either say yes or no, depending on whether he's a knight or a knave. Okay. And I don't care about that. All that I care is if Dikshant, whoever Dikshant is, says yes, I will go to road 2. Okay. This is what my action point is. And if Dikshant says no, I will take road 1. Now, why is this working? This is what we have to understand. Why should this work? Okay, Kavin, go on.
It's because A will not know that what B is going to say, because we can't predict another's one other's person's start. And if A says yes,
one sec. Hold on. A knows who B is. There are two things to take into consideration here. Okay, A knows whether he is a knight or a knave. A knows whether B is a knight or a knave. Okay, this is true, correct? Yes, and also, right, if A is a knight, what he says reflects the truth, and if A is a knave, whatever he says reflects the false thing. Okay, this is something you have to keep in mind. Okay, anyway, let's see, in the interest of time, let's see, what happens, whether it happens. Okay, so now there are two cases to consider. First case is, suppose A is a knight. All right, so if A is a knight, then B is a knave, obviously, because there are two opposite people, right? So let's take the analysis. Now, suppose A is a knight and A says yes. Then what is the situation? If A is a knight and A says yes, what does it mean?
Then we have to take road 2.
It means B is a knave and he will say road 1 leads to freedom. Because a knave says road 1 leads to freedom, it will not lead to freedom. Therefore, take road 2. Make sense? Okay. Yes. Now again, A is a knight and suppose A says no. If A is a knight and A says no, what does it mean? It means that B, the knave, says that road 1 does not lead to freedom. Because
So
a
it will
knave
lead to
says road
freedom.
1 does not lead to freedom, it will lead to freedom, therefore take road 1. Okay. So the case where A was a knight, we have set it. Our action is correct. Okay. Now this should also work if A was a knave in particular. Okay. Then it's an interesting solution, right? So suppose A was a knave now. Okay. Now again think, if A is a knave and he says yes, what does it mean? It means that he says B the knight says yes for the fact that road 1 leads to freedom. Now A is a
Right, then
knave,
answer is
therefore
true.
what does it mean? It's not true, right? So what he actually means to say is that the knight will not say that road 1 leads to freedom. If the knight will not say that road 1 leads to freedom, what should I do? I should take road 2.
Take road 2.
Exactly. Now the last case, if A is a knave and he says no, what does it mean? He means to say that B the knight will not say road 1 leads to freedom. But again, because he's a knave, what he really meant to say was that road 1 will actually lead to freedom, therefore take road 1. Make sense? So this question, this solution works irrespective of whether the person we ask is a knight or a knave. And that is the idea, right? So the solution you find, because it's a case of life and death, it better work under all possibilities, no? Otherwise you may die, right? So this is why your solution must work irrespective of the person who asking is a knight or a knave, okay? All right, I know there are a lot of interesting questions coming up, but Vinay, is it okay if I just proceed now? I'll post the slides.
Yeah. So how much time do you think you'll take?
I think I can finish in 10 minutes flat, end to end.
10
Max.
minutes. Okay.
Max. I will try to
Yes,
finish
yes.
earlier.
But we won't have time for Q&A from students. So I hope that is all right.
I mean, I think they can write to me, give them my email address. They can always write to me. I'm happy to talk.
Sure. That would be wonderful. Thank you.
Okay, so now let me just talk about the application. Okay, so all this is fun. Logic puzzles are fun. But now where does this have an application in theoretical computer science? Okay, the place where this applies is in this area called mathematical logic, which is application in program verification and model checking. Okay, so now what is model checking should be the next question that you should know. Again, of course, there's nothing that Google does not know, but let me say what I know, okay, so that Google will supplement what I say, all right? Okay, so now just to motivate model checking, the 3 people who you see on screen are 3 computer scientists, okay? They are Edmund Clark, Alan Emerson, and Joseph Sifakis. They got something called the Turing Award, okay? Now, do you know what the Turing Award is? Anyone heard of the Turing Award?
Yeah, I've heard of it, but yeah, I
I've
don't
heard
know
of
much.
Turing, but not the Turing Award.
Heard of Turing test.
Yes.
Okay.
I've
So
heard of a Turing machine.
very good. Wow. Yes. So Turing machine was invented by Alan Turing, and this award is constituted in his honor. Okay. So the Turing Award is the biggest award in computer science, just like the Field Medal in mathematics or the Nobel Prize in physics, or
Ma'am,
Nobel
can
Prize
I
in
say something about the earlier thing?
Yes.
Ma'am, if you want to frame a question, ma'am, you can see in any means those logic questions in which we have to ask questions to the people, ma'am. It is like the binary coding, ma'am. All the important terms like road 1, road 1 or road 2 or freedom or death or A or B have to be included in one line. And then the various combinations we have to check whether which combination works.
Absolutely. Yeah. See, I agree with you. So you are already thinking of writing this as a logic formulae, correct?
Yes, ma'am.
Agreed. So I think you have a background in logic already, which is why you're able to say all these things, right? Excellent. Yeah. I agree completely with what you said. But see, I cannot assume that the audience here already has a background to logic, right? So this is why I can only present it as a puzzle and kind of, but do you agree that, when all these people answered, okay, internally they were doing this formulae and solving it, right?
Yes, ma'am.
Okay, great. Okay, so
ma'am, there should be actually 8 cases, but since A and B are variables, means it can be anyone we ask. There is no special, since we do not know whether A is knave or knight, then actually reduces to 4 cases. Means A. Means
okay.
A.
So Very good, very good. So I don't know where you learned logic, but yeah, you seem to have a proper grip on that. So did you learn propositional logic?
No, ma'am, I actually solved a lot of logic questions like that. Then finally one day it struck me that it could happen like this.
Aha, okay, still better. Wow. So without a formal background or training in logic, you figured it out. Amazing. Okay,
Thank you,
great.
ma'am.
Sounds good. Okay, so let's go back to what the Turing Award is, right? The Turing Award is the analog of the Nobel Prize and the Fields Medal. Okay, so it's given only for computer science. The fundamental contributions in computer science get the Turing Award. So these three people whom you see here got this award in 2008 for the technique called model checking. Okay, so therefore it must be something fundamental, something important, right? That is the background. So I have written a why. Okay, why did they get the award? Because model checking is a fundamental contribution. In the next few slides, I'm just going to tell you, what they achieved by model checking without telling exactly what is model checking, simply because I don't have the time. Okay. So I'm going to talk about some real life incidents which happened. Okay. So that you can appreciate why model checking is necessary, why it is an important technique. Okay. Now, what you see here is a machine which is used for administering radiation for people having cancer. Okay. You must have heard of radiation. Okay. People who have cancer, go for radiation treatments. So what happens is that this machine administers some particular doses in some particular areas of the body, depending on where you have the problem. And over a few sitting or doses, people get better. So this particular machine you see here is called Therac 25. The incident happened in 1987. What happened was people died after taking a treatment from this machine. The reason being the machine emitted not the intended dose, but 100 times the dose it should have intended. Okay, because radiation is very strong. It can basically burn your body parts if it is comes in extensive dosages. Okay, so this machine was responsible for people dying, not because they had cancer, but because the machine malfunctioned. Okay, story number one over. I'm proceeding to story number two. Anyway, so the reason for the problem was there was an error in the software of this machine. Okay, now as you can imagine, most of these machines we use day-to-day life have a program embedded inside. Your mobile phone has a program in it. The computers have an operating system. Okay, you think of some flight. Okay, there is a software embedded in it. So basically all of this run on this software. Now if software malfunctions, you're dead. Okay, story number two. You can Google on all these terms. Okay, I'll share the slides. This is the story of a computer, the Intel processor, which many of you would have heard, right? In any of you have a computer at home would have heard of an Intel processor. So there was this professor, a mathematics professor, okay, who was working on some constant called the Brunt's constant. Okay, he wanted to compute this, series you see here. Okay, so he had several machines in his batch, and they're supposed to converge to this number called B. Okay, this B is I've written here, whatever it is. So then one day, he thought of buying the latest Intel machine so that he thought his computations will become faster. He bought a new machine, put in his batch of computers. From that day onwards, his answers all came to be wrong. Okay, when he started to test this. So he got suspicious. He thought, well, my answers were coming okay till now. Maybe they were a bit slow. When I got this fast machine, things all went, berserk. Then he wrote to Intel. He said, I suspect there is a problem with your processor. So Intel knew there was a problem. They were keeping quiet because for the, for people who want to access Facebook and watch a movie, it doesn't matter. Okay, that machine is fine. But for somebody who had to compute something, okay, which was supposed to be precise, it really mattered. So Intel had to accept there was a problem. There was a bug in their floating point unit. And of course, it became a big news, and Intel had to, replace all the processors. Okay, irrespective of people using it only for YouTube and Facebook. Okay, they had to still replace all of them. Story number two. Story number three, what you see on screen is a rocket, okay, which was launched by the European Space Agency. It is called Ariane 5. Now, what happened to this is, okay, this picture I've taken from the internet, obviously. Okay, it was launched on the 4th of June, 1996. 37 seconds after it took off, it just crashed. Okay, it just blew up. Okay. Now, the reason for it was some exception in the software inside this, inside this rocket. Okay, there was some malfunctioning. Okay, some conversion from 64 to 16 was attempted, which should not have been the case. And it just blew up, resulting in a lot of money, whatever. Okay, a lot of reputation. I have two more stories. Now, what you see here is a Toyota hybrid vehicle. So there was a problem in the braking system of this particular prestigious car, because of a software glitch in their anti-lock braking system. Again, as you see, these many number of cars had to be recalled because of this problem. My last story for the day. Okay, this we don't need in India, perhaps a thermostat to, kind of control the temperatures within the houses. But in very cold places, if you keep a thermostat in the house, it keeps your house warm and comfortable at a certain temperature. Now, this Nest is a very famous company which manufactures thermostats. This story is from 2016. It does not mean because I stop here my stories does not mean problems have stopped happening. Just that I need to put a stop somewhere. Okay. So what happened to this thermostat is, in many people's homes, again, a software glitch resulted in people getting frozen inside their homes. Okay. This is a real story. Now, now let's try to take a common story out of all these things, right? What do these stories have in common? Okay. All of them have been either resulting to death or losses, huge losses, or loss of reputation, simply because there was a problem or there is a bug in the software system inside a complicated machine. Okay. Now, how can we stop such things from happening? Is it possible to, let's say, verify, okay, within code, verify the software before you put it in such a complicated, important device? Okay. If it is possible, we should just go for it, right? Are there techniques, algorithms which allow you to verify your software? Okay, now software, when I say it can be now zillions of lines of code, right? Is it possible to verify? Now you may have some properties you may want to check. Okay, does my system satisfy this particular property P? Okay, this is a typical question, right? So now to check this, we need a technique of verification. So model checking, as I suggested earlier, essentially is such a technique which allows you to verify, basically real life systems like this against a property. Now this property is returning some logic. Okay, that's all I can say for now. So model checking essentially is that technique which allows us to verify systems like this so that we can certify up to some level, okay, that this is error free up to so and so point. See, it is still not 100% possible. The reason being that all these systems are humongous. Okay, the number of lines of code is really humongous. So it's not possible to 100% certify them. These fall under infinite state systems. So to certify an infinite state machine, it is humanly not possible. Okay. So that is why the technique is called model checking and not system checking. I am not checking the actual system. Okay, I am abstracting the system into a model, right? In the beginning, we saw graphs for models, right? In a similar manner, I can abstract the system into a model which has finite number of states. And then on that model, I can check if a particular logic property holds good or not. Okay, this is model checking in a nutshell. And that is why they won the Turing Award. So indeed, mathematical logic plays a very important role in formal verification and in model checking. Okay, Diksha, you have a question, and I think I'm going to skip puzzle 5. I will post the slides. I'll encourage you to look at it. Diksha, go on.
If the model checking was invented in 2008, why did the this thing Nest thing happen in 2016? It could have
Very
been
good question. Very good question. Why did it happen? The reason being, see, there are two things here, right? Now, when I make a model, okay, one question you must ask is how many states can your model have? Okay, finally, you are going to run it on a computer, right? You're building a tool, a model checking tool, which takes as input a model and a logic formulae and checks for something. Okay. Now, in 2008, it's possible that the size of the model that your computers can handle was only some n. Okay, now we are able to handle models that are millions of states larger. Okay, we are able to now have more sophisticated algorithms which can handle larger kinds of models, right? So this also says that even though the technique of model checking exists, lot more work needs to be done, okay, in order to be able to get tools which are faster, which can handle larger systems, right? So very good question. Arushi, yes.
Ma'am, I don't know what model checking is, but if like it's some kind of like just verification and that's just matching facts, then wouldn't that be simple? What is it about model checking that makes it like difficult to do?
Okay, imagine a program which is like some 2 million lines of code. Okay. And the properties you have to verify. How will you express the properties you have to verify and check that? Okay, if every property that you have in mind exhaustively is checked on your underlying system. When you say simple, 5 lines of code is simple, 20 lines of code is simple, 100 lines of code is simple. Okay. and the kind of systems that are deployed, right? How can you predict the size of the systems that you're going to deploy a priori?
Oh, okay. I got it. What are properties?
Properties are, let me give you an example, a very, simplistic example of a property. Okay, you have a mobile phone. Okay, now there is a software inside the mobile phone. Okay, a simplistic property I can say is that whenever you get an incoming call, when you do the swipe, the call must connect or whatever. Okay, this is a property. Another property, okay, now you have a computer, right? Every computer has an operating system. Now, would you like if the computer seller tells you that your operating system will work for 5 days, 6th day, I give you no guarantee. You don't like it, right?
Yeah.
Every time you start up your computer, you would expect it to have a smooth startup, no? So this is a property that you want to ensure.
Okay. So it's not like some kind of physical specification. It's like some kind of intrinsic property. Okay, I can get why that will be hard. Okay.
Yeah, in a more better way, you can imagine properties to be safety properties. Okay, safety property is something which says some bad thing will never happen. That is a safety property. Okay. Now, that is not enough. Okay, you need liveness properties also. Okay, we need good things to happen again and again and again, right? For example, in the operating system, every time I start my computer, I want certain background tasks to happen, right? Every single time I start my computer. So that's a liveness property. So certain things I want to say that repeatedly some good things continue to happen. That's a property. Similarly, I want to say that, like in that rocket example, right? I want to say, so maybe the rocket example, the problem happened because some trigger happened and then, some unexpected thing happened at the same time. Okay, it's like A and B together happened. So maybe if you say that it is never ever the case that A and B happen together, maybe you would be good. You see what I mean? So these are examples of properties.
Yes, okay, I got it. Thank you, ma'am.
Okay, so Vinay, I think I'm skipping my 5th puzzle, but maybe I think Tambezar is here. And I think this was again related to cryptography. So I would leave it saying that, okay, number theory plays an important role in cryptography, and cryptography is also an important topic in theoretical computer science. I will leave it at that. I hope that my slides will kind of explain, self-explain, that this last set of slides was just to illustrate the Fermat's little theorem in number theory and say that it's connected to cryptography. That was my only role. Anyway, so the final slide I'll show that in a nutshell, theoretical computer science is essentially a lot of mathematics, okay, which has applications in, day-to-day life. So algorithms, formal methods, games, cryptography, a lot of these things are nothing but mathematics in disguise. So people who love math, go for it. That's all I'll say, okay? As somebody who works in computer science, all that I'll say is people who are good in math should do theoretical computer science, and I'm done. Thank you so much. And sorry for taking 28 extra minutes.
Thank you so much, Krishna, for that wonderful session.
Thank you so much.
I mean, I have a lot of things to share, but maybe I'll talk to you. If you have another 2-3 minutes, we can quickly get into the breakout room and talk.
Yes,
but I'll just invite Swasti to share a feedback and give the vote of thanks.
Sounds good. Yeah, sure.
Thank you, sir. Thank you so much, ma'am, for introducing graph theory in such an interesting and interactive way. Actually, I was a bit hesitant before the session as we are going to learn from a faculty from IIT Bombay. However, it was so engaging that I feel I've started loving this topic. What I like the most is the puzzle 3 because it looked hard, but in reality it is very easy. Once again, thank you so much, Krishna ma'am, for a great
Thank you
session.
so much, Swasti, for your kind words.
Thank you.
Yeah.